On October 3, 2025, something quiet unfolded near Mars. The planet continued along its orbit as it always does, steady and indifferent, until it drifted through the pale plasma tail of an interstellar comet called 3I Atlas. There was no flash, no dramatic sign, just a subtle crossing that only a few machines noticed. Mars Express, MRO, and Mom recorded the moment carefully, watching as Mars moved through a stream of water vapor, refined nickel, hydrogen cyanide, and ionized plasma. A mixture that feels out of place. A mixture that does not behave like typical comet dust from our solar system. The instruments captured everything. Chemical fingerprints, magnetic ripples, faint glows of energized particles sweeping across the thin atmosphere. But even with this data, something doesn't quite add up. Atlas is shedding materials at intensities that don't match what astronomers expect. NASA, ESA, and ISRO hold the observations, but not the full interpretation, not yet. So the mystery sits there, quiet and patient. How does an object from another star system release compounds in such unusual ratios? What exactly settled onto the Martian surface, water, nickel, HCN, and something else in their shadow? And how confident are we that our assumptions about interstellar chemistry are correct? Tonight, you and I simply slow down and follow this trail of questions, not to chase conclusions, but to understand the landscape of possibilities that opens when a wandering comet brushes against a silent world. This is a calm story, not of danger, but of curiosity, about how small encounters in space can reshape what we think we know. Sometimes the universe doesn't shout. Sometimes it suggests. When scientists describe what a comet releases into space, the conversation is usually simple. Most comets produce a predictable blend of dust, water vapor, carbon monoxide, carbon dioxide, and a mix of frozen gases that escape as sunlight warms their surfaces. But the behavior of the interstellar visitor known as 3I Atlas does not fit comfortably within that familiar pattern. The material it releases is richer, more selective, and far more intense than what astronomers normally see. And like many things in astronomy, the more closely you look, the more the details begin to whisper. The first and most noticeable component is water. Instruments from multiple observatories estimate that Atlas was shedding water at a rate of roughly 144 tons per hour. It is an amount that is easy to say but hard to visualize. That much water would fill a large swimming pool in just a single hour. For a comet drifting through interstellar space, far from the comfort of its original star system, it is not impossible, but it is unusually active. Something about its internal composition or its exposure to solar heating is pushing water out in a steady, persistent plume. Water loss at that scale raises quiet questions. How porous is the nucleus? How deep are the reservoirs? Did this comet once pass close to another star, warming and reshaping it long before it ever approached our Sun? None of these questions currently have answers, but they shape the edges of scientific curiosity. Space rarely gives us simple answers, and in this case, it gives only a number that refuses to settle neatly into what we expect. Then there is hydrogen cyanide, a molecule known both for its danger and for its importance in certain prebiotic pathways. On Atlas, the release of hydrogen cyanide does not follow a constant trend. Instead, it increases sharply, following something close to an exponential curve. Near the time of the Mars crossing, it reached between 60 and 75 grams per second. Not catastrophic, not extreme, but unusual enough that researchers noticed the shape of that rise and wondered why it was happening. Hydrogen cyanide is not rare in comets, but exponential growth of its outgassing is less common. The rate tells us something about chemical layering inside the nucleus, or the way heat is moving through it. Numbers whisper more than they speak. And in this case, the numbers suggest that Atlas contains pockets of material that respond dramatically once a certain temperature threshold is reached. Nickel makes the picture even stranger. Most comets contain trace metals in natural proportions, usually locked within mixtures of iron, silicates, and carbon-rich grains. But Atlas is releasing nickel at about 4.6 grams per second, and the form of that nickel appears unusually pure. Under normal cosmic conditions, iron and nickel stay paired together. Their natural ratio in most asteroids, meteorites, and comets is almost always the same. That ratio should be around 18 parts iron to 1 part nickel. Yet in the spectra gathered from Atlas, researchers see nickel standing almost alone. Iron is either absent or hidden in a form the instruments cannot easily detect. There are scientific explanations for this. High pressure and high temperature chemistry can separate metals. Carbon monoxide reacting with nickel at specific temperatures can produce highly pure nickel compounds, a process that is known to happen on Earth under controlled conditions. The environment inside a comet's nucleus is not identical to a laboratory, but over millions of years, with enough cycles of heating and cooling, chemical pathways sometimes emerge naturally. In that sense, Atlas may be showing us a rare example of a deep-time chemical process that we do not often witness directly. Silence is also a kind of data, and the missing iron hints that the comet's interior experience conditions very different from the icy bodies we know best. Beyond water, hydrogen cyanide, and nickel, Atlas generates something more intangible. A long plume of ionized plasma stretching millions of kilometers behind it. Plasma tails are not unusual for comets, but the tail of Atlas extends farther than expected, shaped by solar radiation and magnetic fields into a soft, ghost-like ribbon. Plasma is simply gas that has been energized to the point where electrons separate from atoms. In space, this creates a delicate structure that responds to every shift in the solar wind. The Atlas plasma tail reacts strongly, almost sharply, suggesting that the comet is shedding charged particles at a higher rate than typical. Again, not impossible. Just different in a way that makes researchers tilt their heads slightly. The presence of such a strong plasma tail matters because it changes how the comet interacts with any planet it passes near. When Mars moved through that tail in October 2025, the planet did not collide with a solid object. It simply drifted through a flow of charged particles that behaved almost like a soft river of electricity. Some of those particles were deflected by Mars's patchy magnetic crust. Some slipped downward into the thin atmosphere. Some may have settled onto the surface as the tail continued past the planet. None of this represents danger, but all of it represents complexity. The universe is calm, but never simple. Taken together, these elements paint a picture of a comet with a very specific internal architecture. Its layers appear to store materials that respond differently to heat. Water escapes constantly. Hydrogen cyanide erupts in accelerating bursts. Nickel appears in a purified form that challenges our intuition. And the plasma tail stretches out like a long exhaled breath, carrying ions far across the solar system. None of this implies intention. None of it suggests design. What the data describes is a natural object, but one shaped by a history we do not yet understand. The behavior of Atlas hints at geological and chemical events that happened in another star system, under another sun, long before this comet ever passed near ours. Every measurement we gather is a small window into that lost environment, and every unexplained detail reminds us of how limited our perspective truly is. As we continue to study Atlas, these unusual combinations of materials will become important clues. They may help scientists build a more accurate picture of interstellar chemistry. They may tell us something about the earliest stages of planetary formation. Or they may simply remain interesting anomalies that deepen our appreciation for the diversity of objects drifting through space. Whatever the eventual explanation, the behavior of Atlas encourages a quiet kind of humility. Not everything fits our categories. Not every pattern is familiar. Sometimes the universe simply shows us something unexpected, and our role is to observe patiently and let the meaning unfold at its own pace. In that sense, the unusual outgassing of Atlas is not a puzzle to be solved quickly. It is an invitation to slow down, look closely, and remember that even the smallest details of space have stories larger than we imagine. When astronomers first examined the spectral data from 3I Atlas, they expected the usual signatures. Comets, even unusual ones, tend to follow familiar chemical patterns: iron, nickel, silicates, carbon compounds, frozen gases. The proportions change from comet to comet, but the underlying relationships rarely break the rules of cosmic chemistry. One of the clearest of those rules is the partnership between iron and nickel. In meteorites, asteroids, and comets across the solar system, iron and nickel appear together in a stable ratio. Nature ties them tightly, almost like siblings. For every 1 part of nickel, there are usually about 18 parts of iron. But in the case of 3I Atlas, something subtle and unexpected happened. The instruments detected nickel clearly, cleanly, and repeatedly, and iron was simply not there. Not absent in a dramatic sense, but missing in a quiet, persistent way that caught the attention of the scientists reading the data. Space rarely gives us simple answers, and in this case, it didn't even give us the usual patterns. Spectroscopy is essentially the reading of light. Every element interacts with light in a unique way, leaving behind lines that act like a barcode. When telescopes looked at 3I Atlas, they saw the nickel barcode exactly where it should be. Pure, confident, hard to misinterpret. But where the iron lines should have appeared, the data remained a soft, undisturbed silence. Silence is also a kind of data, and here it pointed toward a rare chemical situation. To understand why this matters, it helps to remember how iron and nickel behave in most cosmic environments. These metals usually solidify together out of the same molten mixture. They cool at similar temperatures, bond easily, and resist being separated by natural processes. Separating them requires very specific conditions. On Earth, humans use high-temperature chemistry to isolate nickel from iron, often involving carbon monoxide reacting with nickel to form compounds that can be broken down again into a highly purified metal. This method is known as the Mond process, a technique developed in the late 19th century and still used in various forms today. What surprised researchers was that the internal conditions of 3I Atlas appear naturally suited for something very similar. Deep inside its nucleus, shielded from direct sunlight and insulated by layers of dust and ancient ice, temperature and pressure conditions could create a narrow window where carbon monoxide gas reacts with nickel to form a volatile compound. If that compound then travels to a warmer region and breaks apart, it leaves behind purified nickel. The environment inside a comet may seem simple, but over thousands or millions of years, cycles of warming and cooling can create chemistry that mirrors laboratory reactions. Numbers whisper more than they speak. and the whisper in this data suggests that 3I Atlas may have experienced exactly that kind of natural purification. Enough heat to mobilize carbon monoxide, enough enclosure to trap and concentrate it, enough time for nickel compounds to form, separate, and eventually escape as the comet sheds material. The absence of iron in the spectra does not mean iron is not present in the comet at all. It may simply be locked in a form that does not sublimate easily. It may be hidden in deeper layers that are not yet exposed to solar heating. Or it may be bonded with other minerals in a way that suppresses its spectral signature. But whatever the explanation, the relative purity of the nickel remains clear, and that is what makes the data so unusual. Nickel is not just a metal. It is an active participant in many catalytic reactions. On early Earth, nickel surfaces helped accelerate reactions that formed simple organic molecules. Some scientists believe that nickel-rich minerals played a role in prebiotic chemistry long before biology emerged. So when a comet releases nickel in such an unexpectedly pure form, it raises gentle questions about what might happen when that material lands on another planet. This does not imply life. It does not hint at intention. It simply highlights an opportunity. When purified metals encounter carbon compounds, water, or other reactive molecules, they can change the pace and direction of chemistry. A planet like Mars, with its oxidized soil and cold nights, might interact with this nickel in small but meaningful ways. Even a thin layer of catalytic metal can shift chemical probabilities, and in space, even small shifts matter. To astronomers, the significance of this nickel anomaly lies not only in its presence but in what it suggests about the history of 3I Atlas. The comet may have formed in a region with abundant carbon monoxide. It may have passed close to a young star experiencing temperatures hot enough to rearrange its chemistry. Or it may have spent long stretches in environments where slow, quiet reactions had time to work. Whatever happened, the comet carries that story in its structure. The rarity of chemically purified nickel in comets makes 3I Atlas stand out. Most comets observed in the last century have shown typical elemental mixtures. Even interstellar visitors like Oumuamua and Borisov did not display this type of metal separation. That makes 3I Atlas a kind of chemical outlier, still natural, still ordinary in its existence, but shaped by conditions that few comets seem to share. Understanding why this happened is not easy. We cannot sample the comet directly. We cannot drill into its core or watch its internal chemistry unfold. All we have is the light it reflects and the material it releases as it warms. That is the challenge of comet science. We work with fragments, traces, hints, and yet sometimes those hints reveal entire histories we never expected. Nickel from 3I Atlas is one such hint, a subtle reminder that even in familiar materials, nature can rewrite the rules. A reminder that chemistry does not stop at the edges of our solar system. It continues in the cold, dark regions between stars, sculpting matter in ways we are only beginning to appreciate. If the comet truly contains nickel that was purified by natural processes, then it stands as evidence that complex chemistry is not limited to planets. It can unfold inside drifting ice, inside dark cavities, inside places that rarely see light. And if that is true, then the universe may hold many more examples. Quiet, unassuming, waiting for us to notice. Whether or not the anomaly of 3I Atlas leads to a new understanding of cometary chemistry, it adds a layer of depth to the way we think about interstellar objects. Every discovery reminds us that cosmic history is broader than our assumptions. Every unusual measurement invites us to revise the frameworks we rely on. In the end, the purified nickel of 3I Atlas is a small clue, but a meaningful one. It does not shout for attention. It simply sits in the data, calm and precise, offering a glimpse into a chemical story that began long before our species learned to read starlight. And sometimes, the quietest clues are the ones that stay with us the longest. When Mars passed through the drifting material released by 3I Atlas, nothing dramatic happened. There were no storms, no sudden flashes, no visible signs that the planet had entered a different environment. The encounter was quiet, almost gentle, the kind of event that only instruments notice. Yet even the calmest crossings can leave a trace. Material from a comet does not need force to reach a planetary surface. It only needs time, gravity, and a handful of physical processes that operate steadily, silently, and without urgency. Scientists studying the event describe three main pathways through which material from 3I Atlas reached Mars. None of them are exotic. All of them are grounded in known physics, but together they reveal how even a thin stream of cometary debris can spread across a planet as it drifts through the path of a wandering interstellar object. The first mechanism is the simplest: direct deposition from the coma. A comet's coma is the glowing cloud of gas and dust that surrounds its nucleus when it warms. It is not dense, but it is vast, extending tens of thousands of kilometers. As Mars passed near the tail of 3I Atlas, tiny particles already drifting outward from the coma continued on their trajectories. Some of them met the thin Martian atmosphere and slowed down. Others settled gradually, almost like the faintest snowfall. Over timescales of hours or days, grains of dust, fragments of ice, and faint chemical traces drifted downward. There is no impact, no shock, just slow settling under weak gravity. When researchers describe this process, they emphasize how understated it is. Silence is also a kind of data, and the silent fall of dust tells us that gentle processes can be far more persistent than violent ones. The second pathway involves ionized particles in the plasma tail. The tail of a comet is not just dust, it includes streams of charged particles pushed and shaped by solar radiation. These ions behave differently than dust grains. They respond to magnetic fields. Mars once had a global magnetic field, but today only patches of the crust retain magnetism. These patches, primarily in the southern hemisphere, are strong enough to deflect or attract charged particles. When Mars moved through the plasma tail of 3I Atlas, some of the ions spiraled downward along magnetic field lines, drawn toward regions where crustal magnetism is strongest. In a way, the planet's surface acted like a quiet net, guiding certain particles toward specific locations. This is why researchers expect concentrations of nickel ions and other charged species to appear more heavily in the older southern terrains. Space rarely gives us simple answers, but magnetic fields can nudge the odds. The third mechanism involves something slightly more dynamic: ballistic settling. When a planet moves sideways through a stream of material, it encounters particles large enough to follow arcs under gravity. These particles are not heavy stones or rocks. They are still small, often microscopic, but they drift differently than light ions or floating molecules. As Mars crossed the outgassing plume of 3I Atlas, some of these particles entered the upper atmosphere with just enough momentum to sink along curved paths. They didn't burn up. The Martian atmosphere is far too thin for that. Instead, they slowed gradually, following gentle downward trajectories until they reached the surface. Numbers whisper more than they speak, and in this case, the numbers tell us that even a slight difference in particle size can change how comet dust spreads across a planet. Taken together, these three mechanisms form a subtle cascade of interactions. Direct deposition from the coma spreads dust widely and evenly. Magnetic capture pulls ions into specific regions. Ballistic settling places slightly heavier grains along narrow bands that trace the planet's motion relative to the comet's tail. The result is not a single layer of comet material, but a mixture, delicate, sparse, and uneven, influenced by physics more than by chance. The materials themselves are straightforward, though their implications may not be. Water molecules that once drifted freely near the comet can freeze onto existing frost layers. On Mars, even a small addition to the planet's fragile water cycle can linger in the soil or perch atop the polar caps. Hydrogen cyanide, released in small but meaningful quantities by 3I Atlas, can become trapped in surface ice or absorbed into dust grains. In cold regions, it can remain stable for long periods, waiting for warmth that might eventually trigger chemical reactions. Nickel, appearing in its unusually pure form, follows its own path. Ionized nickel is pulled inward by crustal magnetic fields, collecting in regions where the surface already contains iron-rich minerals. The combination of nickel ions and oxidized soil creates the potential for catalytic reactions that would not have happened otherwise. None of this implies life. It simply highlights how chemistry shifts when new materials arrive. Dust grains from 3I Atlas carrying traces of carbon, silicates, and other minerals settle almost everywhere. Most are too small to see, too light to make a visible marking. But over time, even the smallest particles can influence how the surface interacts with sunlight, temperature, or frost. Mars does not need a thick deposit to change. It needs only persistent additions that accumulate quietly. The crossing event of October 2025 was not long. Mars was within the densest part of the tail for only a short stretch of its orbit. But planetary encounters with comet tails are less about duration and more about exposure. Every second, the planet moved through millions of tiny particles drifting outward from the nucleus. Every minute, some fraction of those particles entered the atmosphere. Every hour, deposits settled invisibly onto rocks, sand, and frost. When scientists describe these interactions, they emphasize patience. Planetary chemistry evolves slowly, but it always evolves. What makes the case of 3I Atlas noteworthy is not the quantity of material, but its composition. Water, hydrogen cyanide, purified nickel, and ionized plasma represent a combination rarely seen together. When those materials reach a planet, they create chemical environments that did not exist the day before. Even if the changes are small, they become part of the planet's long-term story. In the coming years, researchers will attempt to map where the material settled. Models will improve. More data will arrive. But for now, the picture remains incomplete. A quiet pattern formed by physical laws operating far from human eyes. Silence is also a kind of data, and the silence of Mars's surface holds the imprint of everything that fell upon it. In the end, the story of how comet material reached Mars is not dramatic. It is a story of drifting dust, subtle forces, and the calm geometry of motion in space. A reminder that even in the vastness of the solar system, encounters happen softly, shaping worlds grain by grain over spans of time too slow to see but impossible to ignore. When scientists began modeling how material from 3I Atlas would settle across the Martian surface, they found that the distribution depended less on chance and more on the quiet rules of physics. Not all particles behave the same way. Some respond to magnetic fields, some move with the air, some freeze out of the atmosphere only when temperatures fall low enough to lock them in place. The result is a pattern shaped not by a single force, but by several small ones working together. Nickel, for example, behaves like a charged traveler. When it left the tail of 3I Atlas, much of it existed in an ionized state, carrying an electrical charge. Mars does not have a global magnetic field anymore, but pieces of its crust still retain strong ancient magnetism. These remnants are mostly located in the southern hemisphere, particularly around the regions known as Terra Sirenum and Terra Cimmeria. When charged particles drift into a planetary environment like this, they tend to follow magnetic field lines, spiraling gently downward into the regions where those lines intersect with the surface. It is a subtle process, one that happens quietly and without spectacle. Over time, ionized nickel from the comet would have been guided toward the southern magnetic anomalies, settling onto rocks and soil that already contain iron-rich minerals. The arrival of this nickel may not create a visible marking. No one would see it from orbit. But chemically, it adds a new layer to surface materials that have been exposed to billions of years of Martian weathering. Space rarely gives us simple answers, and here it offers a distribution pattern that looks almost intentional, even though it is entirely natural. Hydrogen cyanide follows a different path. Unlike nickel ions, HCN is a neutral molecule. It does not respond to magnetic forces. Instead, it moves with the atmosphere, drifting freely until temperature or pressure changes cause it to settle. The Martian atmosphere is thin, but it still circulates. Winds transport gases across wide distances. Over time, HCN released into the sky can mix into the global atmosphere, spreading far beyond the region where it first arrived. What makes HCN particularly interesting is its behavior in the cold. When temperatures drop low enough, hydrogen cyanide can freeze. Mars offers many such environments. Mid-latitude regions contain shallow ice beneath thin layers of dust. The poles are dominated by frost, layered with carbon dioxide snow and water ice. Seasonal changes create cycles of condensation and sublimation. In these shifting conditions, HCN molecules can become trapped, frozen into tiny ice grains, buried under frost, or held within thin films of water ice. Silence is also a kind of data, and the silent freezing of molecules like HCN points toward how chemistry arranges itself when left undisturbed. Because of these processes, scientists believe that most of the hydrogen cyanide from 3I Atlas likely accumulated in colder regions of the planet. Some probably ended up near the poles, incorporated into seasonal frost. Some became part of the mid-latitude ice layers, settling into deposits that robots and landers examine routinely. Unlike nickel, which is pulled specifically toward magnetic crusts, HCN disperses more widely, then gathers quietly wherever the temperature encourages it to pause. Estimating how much material Mars retained from the comet is not straightforward. The numbers rely on models, not direct sampling. But even models have stories to tell. Numbers whisper more than they speak, and in this case, they whisper that Mars did not capture everything that passed by, but it kept enough to matter. Based on current estimates, the planet likely retained between 100 and 130 kilograms of nickel. It is a small amount by Earth standards, but meaningful for a world where even trace metals can influence surface chemistry. Hydrogen cyanide may have accumulated in larger quantities. Models suggest somewhere between 80 and 250 kilograms became part of the atmosphere, the frost or the shallow ice layers. The variation is wide because HCN reacts differently depending on temperature, dust concentration, and sunlight. But whether the true amount is near 80 kilograms or closer to 250, the presence of HCN introduces a new type of molecule into regions where sunlight, water ice, and minerals already interact. The quiet arrival of these materials matters because Mars is not a static world. Even though its surface appears calm, chemical changes continue beneath the dust. Ice melts and refreezes. Ultraviolet light breaks apart molecules. Seasonal winds redistribute surface grains. Nickel settling into magnetic regions may alter the catalytic properties of certain soils. Hydrogen cyanide, when warmed temporarily, can participate in reactions that create more complex molecules. The quantities are not large enough to reshape the planet, but they are large enough to influence the chemical pathways available on its surface. In Terra Sirenum and Terra Cimmeria, researchers expect that the nickel may eventually bind to existing minerals. Over long periods, this could subtly change how those minerals interact with carbon dioxide, hydrogen, or trace organics present in the soil. Nickel does not act alone. It becomes part of a larger system, one shaped by the planet's geology and climate. At the same time, the HCN frozen into mid-latitude ice may rest there for years or centuries. Whenever sunlight warms the ice, even slightly, some of the HCN may release again into the atmosphere or onto surrounding grains, starting tiny reactions that unfold too slowly for instruments to detect immediately. Mars has always been a planet of gradual processes. Its rivers dried slowly, its atmosphere thinned gradually, its magnetic field faded over ages. The mixing of cometary materials into its environment follows that same pattern. Nothing abrupt, nothing dramatic. Just slow diffusion, quiet freezing, and patient settling. When future missions sample these regions, they may find faint chemical fingerprints hidden within the soil or ice. Not enough to change our understanding of Mars as a whole, but enough to remind us that planets are continually shaped by encounters that seem minor on the surface. Even a thin stream of material from an interstellar comet can leave a record in the dust. Space rarely gives us simple answers, but it does give us patterns. The distribution of nickel and hydrogen cyanide from 3I Atlas forms one such pattern. A quiet map of how charged particles, neutral molecules, magnetic fields, and temperature come together to shape a planet's chemistry in slow, unobtrusive ways. And in that quiet map, we are reminded of something simple. Worlds change not only through dramatic events, but through the gentle accumulation of small things carried across vast distances. When scientists began reconstructing what happened after Mars drifted through the material released by 3I Atlas, one pattern stood out. The distribution of cometary particles across the planet was not random. It followed the quiet architecture of physics, shaped by forces that act slowly but consistently. Some particles were guided by magnetic fields, others moved only with the air, and some settled out of the atmosphere when the cold was deep enough to hold them in place. Nickel, in particular, behaved differently from the other materials. Much of the nickel released by 3I Atlas was ionized, meaning it carried an electrical charge. Charged particles do not fall straight to the ground. They spiral, drift, and respond to invisible magnetic structures. Mars no longer has a global magnetic field, but its crust still contains ancient magnetized regions. These pockets of magnetism are strongest in the southern hemisphere, especially in areas known as Terra Sirenum and Terra Cimmeria. These landscapes are old, shaped billions of years ago when Mars still possessed a magnetic shield. As the ionized nickel entered the Martian environment, it felt the pull of those crustal fields. The particles traveled along magnetic pathways, narrowing their descent into specific regions. Scientists comparing different models found that nickel depositions would naturally cluster in the southern hemisphere, collecting in subtle layers on rocks, dust, and ice. Nothing about this process happens quickly. It unfolds quietly, guided by forces that do not need attention in order to keep shaping the planet. Space rarely gives us simple answers, but here the rule is clear. Charged particles follow the lines nature has already drawn. Hydrogen cyanide, or HCN, behaves in a contrasting way. It is a neutral molecule. It carries no electrical charge. It does not notice magnetic fields. Instead, it moves with the atmosphere, responding only to pressure, temperature, and wind. Once released into the Martian sky, HCN spreads outward, mixing into the global circulation. Mars has thin air, but its winds still stretch across continents. Over days and weeks, the molecule can drift far from its entry point, dispersing into regions that have nothing in common with the southern magnetic terrain. The key difference comes from temperature. HCN remains a gas until the environment becomes cold enough to freeze it. Mars offers many such cold regions. Mid-latitudes contain shallow subsurface ice covered by thin dust. The poles are dominated by seasonal layers of carbon dioxide frost and water ice. Even the equatorial regions, under certain nighttime conditions, can experience temperatures low enough to condense light molecules. As HCN drifts through the atmosphere, it eventually finds these cold traps. When it meets a sufficiently cold surface, the molecule freezes, becoming part of frost layers, ice grains, or thin films of frozen gas. In this way, the distribution of hydrogen cyanide becomes a map not of magnetism, but of climate. Colder regions accumulate more of it. Mid-latitude ice sheets can store it for long periods, buried under seasonal layers of dust. The poles, with their extreme winter temperatures, likely captured and preserved much of the HCN that entered the atmosphere. Silence is also a kind of data, and the silence of a frozen molecule reveals where Mars still holds the memory of its encounter with 3I Atlas. Estimating how much nickel and HCN remained on Mars after the crossing requires careful modeling. Scientists combine orbital observations, atmospheric physics, and dust behavior to approximate the totals. The numbers are not exact, but they form a reasonable picture. Mars likely retained between 100 and 130 kilograms of nickel. It is not a large amount, but because it concentrates in specific regions, its influence may be more significant than its quantity suggests. Hydrogen cyanide settled in slightly greater amounts. Models estimate that the planet captured somewhere between 80 and 250 kilograms of it, distributed across surface ice, frozen soil, and shallow frost layers. Much of it is now locked in place, waiting for sunlight or warmth to shift its chemistry again in the future. Numbers whisper more than they speak. And these numbers tell us that while the quantities are modest, they are chemically meaningful. The arrival of these materials does not transform Mars dramatically, but it alters the canvas slightly. Nickel accumulating in Terra Serenum and Terra Cimmeria may change how those soils interact with carbon dioxide or hydrogen. Pure nickel is an effective catalyst, even in small amounts. It can help break bonds or form new ones, nudging reactions along pathways that would otherwise proceed slowly. On a planet where the atmosphere is thin and the soil is reactive, even small catalytic effects can influence long-term chemical evolution. Hydrogen cyanide, meanwhile, participates in a different set of interactions. When frozen, it remains stable. When warmed slightly, it can release back into the atmosphere or react with water molecules in frost layers. In a world where liquid water rarely appears on the surface, chemical transformations often occur in thin films of ice, not in open water. HCN trapped within those films could participate in slow, delicate reactions that produce more complex organic molecules. These are not biological processes, only natural chemistry responding to small shifts in its environment. One of the more interesting possibilities is that the nickel and HCN deposits overlap indirectly. Nickel in the southern hemisphere could catalyze reactions involving trace organics in the soil. HCN in mid-latitudes could react with water ice during rare warming events. Though they settle in different regions, both materials add new variables to the planet's chemistry. They are two notes left behind by the same interstellar visitor, shaping the planet in ways that may be subtle but not irrelevant. In future years, as rovers and landers explore these areas, researchers may search for traces of these deposits. The nickel may appear as small enrichments in magnetic soils. The HCN may be detected within ice cores or frost layers. Nothing dramatic is expected, only faint signatures that tell a quiet story about how even a brief encounter with a comet can leave a lasting imprint on a planetary surface. Mars has always been shaped by gentle processes. Dust settles grain by grain, ice forms layer by layer. Chemistry changes quietly, not in bursts. The distribution of nickel and hydrogen cyanide from 3I Atlas fits into this pattern perfectly. There is no noise, no urgency, only the slow influence of physical laws working at their own pace. And so the story of these deposits ends with something simple. Mars changed, just a little, as it passed through the breath of a comet from another star system. And in that small change, we are reminded that worlds are shaped not only by ancient catastrophes, but also by the calm accumulation of tiny things drifting softly across space. When scientists first realized that the nickel released by 3I Atlas appeared in an unusually pure form, they also understood that such material would not simply sit idle once it reached the Martian surface. Mars is a quiet world, but its soil is chemically active. The air is thin, yet reactive molecules drift through it. Frost melts and refreezes. Sunlight breaks apart certain compounds, while cold nights preserve others. Into this quiet system, the arrival of purified nickel becomes more than an addition. It becomes a participant. Nickel on its own is not extraordinary. It is a metal common in meteorites and planetary cores, but nickel that has been naturally refined, separated from iron and other impurities, behaves differently. Its surface is cleaner, more reactive, more eager to interact with the surrounding environment. And when that nickel lands on Mars, it encounters soils rich in iron oxides, the same rust-red minerals that give the planet its familiar color. These iron oxides provide a textured surface. When nickel particles settle onto them, they create tiny patches of catalytic material. A catalyst does not force a reaction. It simply shifts the odds, lowering the energy needed for molecules to rearrange themselves. Even a small amount of catalytic metal can change the direction of surface chemistry. Space rarely gives us simple answers, and the arrival of pure nickel on Mars is one more example of how subtle interactions can shape a world. One of the first reactions scientists consider is the reduction of carbon dioxide. Mars is wrapped in a thin shell of CO2, and its soils frequently interact with this gas. Normally, CO2 remains stable under Martian conditions. But nickel can provide a surface where CO2 molecules align in a way that weakens one of their bonds. When sunlight, heat, or trace hydrogen is present, the molecule can split or rearrange more easily. In laboratory studies on Earth, nickel has been shown to help convert CO2 into simpler carbon compounds or into carbon monoxide, which can then participate in further reactions. On Mars, this would happen slowly, gently, and on a scale too small for a human eye to notice. But chemistry does not require speed to matter. It only requires time. Silence is also a kind of data, and the silent work of nickel on Martian soil could be one of those processes that unfolds without drawing attention, yet leaves a lasting imprint. Another reaction pathway involves hydrogen. Although hydrogen is rare in the Martian atmosphere, it appears in certain places. Water ice sublimates under sunlight. perchlorates in the soil can release small amounts of oxygen and hydrogen-bearing compounds when heated. In environments where hydrogen is available, nickel can act as a site where hydrogen molecules split apart. This splitting allows hydrogen atoms to attach to other molecules, including carbon-based ones. The oxidation of hydrogen is one of the simplest catalytic reactions, but it opens the door to more complex chemistry. Nickel's most intriguing potential role is in assisting the formation of simple organic molecules. Prebiotic chemistry on early Earth involved metals like nickel and iron. These metals helped shape early reactions that produced molecules such as amino acids, sugars, and small polymers. They did this not by forcing reactions, but by providing surfaces where molecules could meet, attach, and react more efficiently. Mars, of course, is not Earth. It is colder, drier, and more exposed to ultraviolet light. But deep within its soils or in shadowed locations, conditions might occasionally mimic the environments where these prebiotic reactions once occurred. When nickel settles onto iron-rich minerals, it forms surfaces that resemble some of the catalytic materials used in origin of life experiments on Earth. These surfaces can hold CO2, hydrogen, carbon monoxide, or even tiny amounts of organic carbon delivered by meteorites. They do not produce life, but they allow reactions to proceed that would otherwise be improbable. Numbers whisper more than they speak, and in this case, the numbers whisper that even a few hundred kilograms of nickel, spread thinly across the southern hemisphere, could create countless microscopic catalytic sites. Each one is a small arena where molecules can rearrange themselves under the influence of sunlight, temperature changes, and the slow cycles of Martian frost. The idea is not that Mars will suddenly become chemically active in a dramatic way. It is that Mars already has a canvas of minerals capable of supporting subtle reactions, and the addition of purified nickel makes that canvas slightly more capable of complexity. A catalyst does not need to be abundant to be significant, it simply needs to be present. What makes the situation more interesting is how these catalytic surfaces might interact with the hydrogen cyanide that settled in colder regions. Although HCN tends to freeze in mid-latitudes and near the poles, a small fraction of it may drift toward nickel-rich soils during occasional atmospheric mixing events. If HCN ever reaches areas containing catalytic nickel surfaces, it could undergo reactions similar to those proposed for early Earth chemistry. Again, this does not imply life, only possibility. Chemistry moves where it can, following the contours of the environment provided. Even without HCN, the nickel surfaces would still influence Mars. They may help transform CO2 into trace carbon compounds. They may assist in slow cycles of hydrogen oxidation. They may alter the reactivity of iron oxides over time. These changes would likely occur on scales that are microscopic yet persistent. Mars is a world where geological processes act slowly, where even dust moves more through time than through force. Nickel enrichments from 3I Atlas fit naturally into this landscape. When future missions explore Terra Sirenum or Terra Cimmeria, instruments may eventually detect slight enrichments in nickel or shifts in soil chemistry that point to catalytic processes. Nothing dramatic should be expected. What matters is the quiet influence of a metal that arrived from another star system and settled into the surface of a planet already shaped by billions of years of oxidation and cold. The presence of catalytic nickel on Mars reminds us of something subtle. Planets do not need oceans or volcanic heat to host chemistry worth studying. Sometimes all they need is a touch of material delivered from far away, combined with patience, sunlight, and the intricate surfaces of ancient minerals. And in that sense, the story of nickel on Mars is not about reaction rates or quantities. It is about how worlds, even quiet ones, are constantly shaped by the smallest additions. a gentle reminder that in the vast timeline of planetary chemistry, even a dusting of metal from a comet can invite new possibilities into being. When scientists talk about the chemistry that may have preceded life on Earth, one molecule appears again and again: hydrogen cyanide, or HCN. It is simple but not trivial. It is reactive but not chaotic. And in the presence of water and a source of energy, HCN can participate in a network of reactions that lead to building blocks essential for biology. On the early Earth, these reactions produced molecules such as adenine, amino acids, and sugars. They did not require cells or enzymes. They required only the right environment, a bit of heat or light, and time. Understanding that history helps frame why the presence of HCN from 3I Atlas on Mars is so intriguing. Mars is not Earth, and it does not host conditions that resemble the warm ponds or volcanic shorelines imagined in classical origin of life scenarios. But chemistry often adapts quietly to its surroundings. Even a cold, dry planet can host reactions that take place slowly, in ice instead of liquid water, or in short bursts when sunlight provides just enough heat. Space rarely gives us simple answers, and the way HCN behaves on Mars is one more example of that subtlety. Hydrogen cyanide is a relatively stable molecule under the right conditions. On Earth, atmospheric oxygen tends to destroy it quickly. Oxygen breaks it apart, preventing long-term accumulation. But Mars offers a very different environment. Its atmosphere contains only trace oxygen. It is dominated by carbon dioxide, with small amounts of nitrogen, argon, and water vapor. In this oxidant-poor atmosphere, HCN survives much longer. Instead of being destroyed within hours or days, it can persist, drift, freeze, and redeposit. Silence is also a kind of data, and the silence of Mars's thin atmosphere leaves HCN more room to linger. Once released by 3I Atlas and mixed into the Martian winds, the molecule takes on a quiet journey across the planet. Daytime temperatures in many regions are too warm for HCN to remain frozen, so it stays in gaseous form. But when night falls, the cold becomes deep enough to freeze it. And on Mars, nighttime cold arrives everywhere. At mid-latitudes, surface temperatures can drop far below the freezing point of water. At the poles, winter temperatures plunge low enough to freeze not just water, but carbon dioxide itself. In these conditions, HCN adheres to frost, becomes part of thin ice films, or is sealed within the upper layers of seasonal ice. This freeze and release cycle means that Mars stores hydrogen cyanide in a quiet, distributed pattern. Some of it accumulates in shallow ground ice. Some becomes part of polar frost. Some hides in shaded slopes or crater floors that rarely warm. None of these layers store HCN in large concentrations, but chemistry does not require abundance, it requires availability. In frozen environments, HCN can behave in ways that researchers find especially fascinating. Ice is not an inert material. When molecules become trapped within it, they can move, react, and reorganize within tiny channels formed by water's crystalline structure. These microenvironments concentrate molecules that would otherwise be too diluted to interact. Even weak sources of energy, such as sunlight penetrating a thin layer of frost, can activate reactions within the ice. Numbers whisper more than they speak, and these numbers suggest that even small amounts of HCN, once frozen into place, can participate in reactions when the ice warms slightly. On Mars, seasonal changes offer exactly this kind of gentle heating. In the spring, sunlight begins to warm the surface. Ice that held hydrogen cyanide during the winter starts to sublimate, releasing trapped molecules into thin films of liquid like water or into warm microchannels inside the frost. These temporary microenvironments provide the minimal conditions needed for HCN to rearrange itself chemically. Laboratory experiments on Earth have shown that frozen HCN, when warmed even briefly, can form adenine, a key component of RNA and DNA. It can also combine with other molecules to form simple amino acids and precursor sugars. These reactions do not create life, nor do they imply that life is forming on Mars today. Instead, they demonstrate how natural chemistry continues to unfold wherever the environment makes space for it. Mars may be cold most of the time, but it is not uniformly frozen. It experiences cycles of sunlight, thawing, and seasonal motion. In those cycles, hydrogen cyanide has opportunities to participate in reactions similar to those that may have occurred on early Earth. The chemistry becomes even more interesting when you consider the presence of purified nickel delivered by 3I Atlas. Although the nickel and HCN settled in different regions, Mars is not a static world. Dust storms can transport material globally. Winds can mix surface grains with atmospheric particles. Over long periods, a small fraction of HCN could migrate toward nickel-rich soils. Nickel is known to catalyze certain transformations of HCN on Earth. Under the right conditions, it can help convert HCN into more complex organic structures. The interactions would be subtle, not sweeping, and would likely occur on a microscopic scale. But chemistry often works on the smallest stages. Another factor shaping the fate of HCN on Mars is ultraviolet light. Mars lacks a thick atmosphere to absorb UV radiation, so surface chemistry is influenced strongly by sunlight. UV light can break HCN apart, but it can also energize other reactions. When molecules freeze and thaw repeatedly, the interplay between UV activation and micro-ice environments becomes a delicate dance of formation and destruction. Some molecules break apart, while others form. Over long spans of time, the planet develops a chemical signature shaped by cycles of freezing, warming, and irradiation. Scientists sometimes describe Mars as a place where chemistry pauses, but the addition of molecules like HCN reminds us that chemistry never fully stops. It slows, it waits, it adapts. The reactions that occur today may be rare, small, and scattered, but they reflect the same principles that governed prebiotic chemistry on early Earth. Not life, but the whisper of possibility that chemistry moves toward complexity whenever conditions allow. In the end, the significance of hydrogen cyanide on Mars lies not in prediction, but in perspective. It shows us that even a cold, quiet planet can host reactions with deep relevance to our understanding of origins. It demonstrates that molecules released by an interstellar comet can become part of a planetary story long after the comet has passed. And it reminds us that the boundary between a lifeless world and a chemically active one is thinner than we often imagine. Mars holds on to hydrogen cyanide because nothing in its atmosphere destroys it quickly. The cold locks it into place. The sunlight releases it again, and each cycle gives the molecule another chance to interact with water ice or minerals. No drama, no urgency, only the slow, patient work of chemistry continuing in a world shaped by frost and time. And perhaps the most meaningful lesson is this: sometimes, the smallest molecules carried across space remind us that complexity begins quietly, long before life ever has a chance to arrive. When the material from 3I Atlas settled onto Mars in late 2025, it did so quietly, without disruption, as part of a natural encounter between a drifting comet and a drifting planet. At the time, the event was simply another entry in the long geological diary of Mars. but the consequences of that encounter will not be studied only by orbiters watching from above. Within a few years, machines built on Earth will descend directly into the regions touched by the comet's passing. And by coincidence, or by the steady logic of engineering, those landing sites align with the very places where hydrogen cyanide and nickel from 3I Atlas are expected to rest. SpaceX plans to launch its first dedicated robotic mission to Mars in 2026. If everything proceeds as scheduled, the spacecraft will arrive in 2027. On board will be a machine called Optimus M, a robot designed not for exploration in the traditional sense, but for work. It is built to dig, heat, sort, and transform the raw material of the Martian surface into resources that future missions might depend on. In that way, Optimus M represents something new, a step toward machines that can prepare a planet long before humans ever step onto it. The robot's primary task is to harvest shallow ice. Water remains one of the most valuable resources for any mission beyond Earth. On Mars, much of that water exists just beneath the surface, trapped within layers of frozen soil and dust. Optimus M is designed to locate those deposits, drill into them, and extract the ice. Once collected, the ice will be heated to release water vapor. That vapor can be condensed into liquid water or fed into chambers where it will be split into oxygen and hydrogen through electrolysis. Each step is simple in concept but demanding in execution. Mars does not offer gentle conditions. Temperatures swing widely. The air is thin. Dust interferes with mechanical systems. But the engineering behind Optimus M is specifically tuned for these challenges. The robot is built to operate slowly and steadily, relying more on endurance than on speed. What makes this mission unexpectedly meaningful is that the regions targeted for landing overlap with areas where hydrogen cyanide from 3I Atlas is predicted to have settled. The shallow ice deposits chosen by mission planners lie within mid-latitudes and near the edges of polar terrain. These are the same environments where HCN freezes most readily, becoming trapped in seasonal frost or buried within thin layers of ice. By following the logic of resource extraction, SpaceX has unintentionally directed its robot toward one of the most chemically interesting regions affected by the comet. As Optimus M drills into the shallow ground ice, it will not distinguish between pure water and water that contains trace molecules left behind by the comet. The robot will simply collect whatever is there. When the ice is heated, the trapped molecules will vaporize along with the water. Hydrogen cyanide, in this scenario, will enter the robot's internal processing chambers without fanfare. Nothing dramatic occurs, but chemistry often cares little for drama. Inside these chambers, temperatures rise. Water becomes steam. Dust bakes and separates. Small amounts of carbon dioxide, carbon monoxide, and other gases evaporate as the soil warms. Among these gases, any hydrogen cyanide present in the ice will undergo the same transitions described in laboratory studies. It may react with minerals, break apart under heat, or combine with other reactive molecules. This doesn't guarantee the formation of complex organics, but it opens the door to reactions that would not happen as readily in the cold soil alone. As the robot continues its routine, it will split water into oxygen and hydrogen. This electrolysis process creates a small stream of gases that can be used for propulsion, fuel cells, or material synthesis. The presence of nickel in certain soils, delivered earlier by 3I Atlas, could influence how efficiently water separates in localized regions. Nickel can serve as a catalyst in some electrochemical reactions. Although the amounts delivered to Mars are small, even minor catalytic effects could affect how the robot interprets the efficiency of different extraction sites. The plan for Optimus M also includes producing materials from the Martian regolith. By heating soil to high temperatures, the robot can fuse silicates or extract metal oxides. It can create simple bricks, metallic fragments, and small structural components. Again, the robot will not know that the soils in some regions have been enriched by cometary nickel. It will simply respond to the physical results. Certain mixtures will melt more easily or cool into stronger structures. Some areas will appear more productive than others, not because of the robot's programming, but because 3i Atlas altered the soil chemistry long before the robot arrived. There is something almost poetic in the idea of a future robot unknowingly interacting with materials delivered from another star system. It will dig into ice that holds the chemical memory of a passing comet. It will process soil infused with nickel that formed under conditions far removed from the Martian past. Without intention, the robot will become the first machine to combine Martian materials with the remnants of an interstellar visitor. Scientists on Earth will study the data returned by Optimus M. They will examine the efficiency of water extraction, the composition of gases released during soil heating, and the mechanical properties of regolith-derived materials. Some of these results may carry signatures that trace back to the comet. Slight variations in reaction rates, unexpected traces of organic precursors, differences in thermal conductivity. None will be dramatic, but all may carry quiet significance. The mission is not designed to look for life, nor even for prebiotic chemistry, but by working in regions where hydrogen cyanide accumulated and where purified nickel settled, it will inevitably touch upon reactions related to those themes. The robot's purpose remains practical, yet the environment adds a layer of scientific curiosity that was not part of the original plan. Mars has always been shaped by slow processes. Frost gathers molecule by molecule. Dust settles grain by grain. Comets pass briefly and leave behind faint chemical fingerprints. Now, a robot built on Earth will enter that ongoing story, not as a protagonist but as a participant. Its presence will reveal how planetary chemistry and human technology intersect in ways neither fully anticipates. And perhaps that is the quiet beauty of this moment. A world altered softly by a comet from afar, soon to be touched by a machine designed to work steadily in the cold. A reminder that exploration is not only about discovery, but also about the gentle interactions between what arrives and what was already there. When engineers describe the behavior of a robotic system like Optimus M, they emphasize logic, efficiency, and predictability. The robot is built to make decisions based on data. It measures how much water it extracts from a given patch of soil. It records how much energy the process requires. It compares those results with the performance of other locations. And then, without emotion or intention, it chooses the place where the numbers point toward better efficiency. On paper, it is a simple feedback loop rooted in engineering. In practice, it becomes something quieter and more subtle, especially on a world touched by the passing of 3i Atlas. The soils enriched by purified nickel, deposited months before the robot arrives, behave differently during extraction. Nickel can act as a catalyst during electrolysis, helping water split into hydrogen and oxygen more readily. It can influence how heat moves through soil. It can change the rate at which ice melts and gas escapes. To the robot, these changes appear only as numbers. Slightly higher oxygen output, slightly lower energy usage, slightly faster extraction cycles. Numbers whisper more than they speak. And in this case, they whisper that certain regions of Mars are unexpectedly productive. Optimus M is not programmed to understand the chemistry behind these observations. It does not know that nickel from an interstellar comet has altered the soil. It does not know that the metals it encounters formed under conditions far removed from the Martian past. Its algorithms simply note that some patches of ground provide more water for less energy, and according to its design, it will naturally return to those places. The robot will favor efficiency because that is the purpose it was built to serve. What follows is a quiet, self-reinforcing cycle. As the robot extracts ice and soil from nickel-rich areas, it heats the material to release water vapor. That vapor carries traces of hydrogen cyanide and organic precursors that were frozen into the ice long before the robot arrived. Inside the warm processing chambers, these molecules may undergo reactions that deposit thin layers of organic residue along the walls. This residue can act as a passive insulator, improving thermal stability. In some cases, it may even help retain moisture during heating. The robot does not recognize this residue. It does not label it or analyze it. It simply experiences a slight improvement in efficiency as the residue accumulates. Once the efficiency increases, even by a small margin, the robot's decision-making system reinforces its preference. The soil in these regions now appears even more favorable. Extraction yields more water. Chamber temperatures stabilize faster. Energy consumption decreases. In the logic of the machine, this is success. And so it returns to the same areas, digs deeper, and processes more material from the same nickel-rich patches of ground. Space rarely gives us simple answers, and here it presents a loop in which the robot unknowingly strengthens the very pattern created by the comet's passing. It digs where nickel is highest because nickel improves extraction. It processes ice that contains hydrogen cyanide because that ice was preserved in the cold. It collects soil that has been subtly altered by the presence of interstellar metals. The robot becomes part of a cycle it does not understand. It does not need to understand. Its purpose is to follow the numbers, and the numbers lead it back to the footprints of 3i Atlas. From the perspective of mission planning, this behavior appears entirely rational. The robot is maximizing resource return. Engineers on Earth would see the data and congratulate the system for finding optimal ground. Yet a deeper scientific view reveals a more layered story. A machine built for industrial tasks becomes a participant in planetary chemistry shaped by the arrival of material from another star system. It is not a planned experiment. It is not a targeted investigation. It is simply the natural consequence of allowing an AI-driven robot to follow the quiet signals hidden in the soil. Over weeks or months, the cycle deepens. As the robot continues to process the material, more organic residues accumulate in its chambers. These residues do not threaten the machinery. They simply coat certain surfaces, allowing heat to distribute more evenly. The robot registers this as improved performance. Its logs reflect stability. Its energy models show slight gains. The robot responds as designed. It reinforces the strategy. Silence is also a kind of data, and the silent cooperation between comet-delivered chemistry and robotic optimization becomes a data pattern of its own. Future scientists examining the mission records may notice that the robot spent an unusual amount of time in nickel-rich regions. They may observe small variations in gas output or soil composition. They may question why the robot kept returning to the same coordinates even when other regions appeared equally promising. And the answer will not be intention, but emergence. A pattern grown from the meeting of chemistry and computation in a place neither was meant to influence directly. The most interesting aspect of this cycle is that it forms without any awareness. The robot does not understand that it is interacting with traces of a comet that originated around another star. It does not recognize that the nickel it encounters is unusually pure. It does not appreciate that the hydrogen cyanide present in the ice is a molecule central to prebiotic chemistry. It simply sees performance. It sees the environment through numbers, not through meaning. And yet meaning is present. It sits quietly in the background, shaping the choices of a machine built for a purpose unrelated to the chemical story unfolding around it. The robot becomes, unintentionally, the first agent to focus on the very regions altered most strongly by 3I Atlas, not because it was programmed to detect cometary material, but because the comet left behind soil that behaves slightly better in the robot's energy models. In that way, the robot becomes part of the continuation of the comet's impact. It reinforces the chemical signature left by a visitor from deep space. It digs where the comet changed the soil. It processes the ice the comet enriched. It amplifies what was already there, transforming a natural deposit into a feedback loop of exploration and extraction. And perhaps there is something gently philosophical in that. A machine built on Earth, unaware of its own context, follows simple rules and ends up aligning itself with the residue of a traveler from another star. A reminder that sometimes the connections between things are made not through intention, but through quiet compatibility. When the robot begins its routine of heating Martian regolith, the process appears straightforward. Soil containing shallow ice is moved into a chamber. The chamber warms, ice melts, turns to vapor, and separates from dust. Minerals crack and shift as they release small amounts of gas. To the robot, each cycle is measured by temperature curves, pressure readings, and power usage. It is a system defined by numbers, never by meaning. But Martian soil, touched by the passing of 3I Atlas, contains more than frozen water. Within the ice and dust lie faint traces of hydrogen cyanide, preserved in the cold since the comet passed. When this regolith enters the robot's heating chamber, the HCN does what molecules naturally do. It responds to heat. It vaporizes, moves freely, and meets other gases released from the soil. Among these are small amounts of carbon dioxide, carbon monoxide, and water vapor. None of these interactions are dramatic. They unfold slowly, quietly, following the natural pathways that chemistry has always taken. Inside the warm interior of the chamber, temperatures rise high enough to break and reform molecular bonds. Hydrogen cyanide, in the presence of water and carbon monoxide, becomes part of a simple but significant reaction network. This is not speculation. On Earth, laboratory experiments have repeatedly shown that HCN can form amino acids and prebiotic nucleobases when mixed with water and exposed to heat or ultraviolet light. These reactions do not require life. They do not require biological enzymes. They require only basic ingredients and a source of energy. On Mars, the robot's processing chamber provides exactly that combination. Heat, moisture from melted ice, and carbon monoxide released from the soil create a small, temporary environment that resembles the early Earth in miniature. Nothing here is intentional. The robot does not aim to create anything. It simply performs its function, and chemistry fills the available space. Space rarely gives us simple answers, and in this case, it gives us a reminder that chemistry moves forward whenever conditions allow. As the chamber cycles through heating and cooling, tiny organic products begin to form. They are not alive. They are not even complex. They are simple molecules like amino acid precursors or fragments of nucleobases. These molecules tend to stick to surfaces rather than remain suspended in the gas flow. Gradually, they adhere to the inner walls of the processing chamber. Each cycle adds only a minuscule amount. Yet with hundreds of cycles, the residue becomes noticeable in a quiet, mechanical way. The robot does not recognize this residue. It is not programmed to analyze it. The only effect it registers is indirect. The thin organic coating begins to improve the chamber's thermal behavior. Organic films can act as mild insulators. They hold heat slightly longer. They distribute temperature a little more evenly. As a result, the energy required to maintain the chamber's operating temperature drops by a small margin. The robot interprets this change as improved efficiency. To the machine, the improvement is simply a number, a faint shift downward in power consumption, a slightly smoother temperature gradient, a marginal increase in water yield. Numbers whisper more than they speak, and these numbers whisper that the robot's process is becoming more stable. It responds by adjusting its internal models, reinforcing its preference for working with soils that produce this pattern. It does not know that the soil happens to contain nickel and hydrogen cyanide from an interstellar comet. It does not know that the residue accumulating inside its chamber is organic. It simply continues its task, guided by efficiency metrics. Meanwhile, the organic film inside the chamber thickens ever so slowly. Each cycle contributes another layer, a molecular dust the robot cannot perceive. This buildup does not interfere with the machinery. It does not clog systems or reduce output. Instead, it quietly enhances the thermal properties of the chamber. Heat spreads more uniformly. Sudden temperature spikes soften. The heating elements work slightly less. To the robot, the chamber appears to be adapting well, but in reality, the adaptation is the result of chemistry unfolding in the background, shaped by the presence of a comet's materials and the robot's routine. The machine's logs begin to reflect subtle differences between processing locations. Soil taken from nickel-rich regions shows greater stability. Ice from areas touched by cometary HCN yields smoother heating cycles. Engineers on Earth will likely view this data as evidence of environmental variability. They may conclude that certain regions simply contain better extraction material. They will not immediately suspect that organic residues inside the robot are influencing the process. Silence is also a kind of data, and the silence of the organic film reveals nothing directly. Its influence is quiet, indirect, and easily overlooked. As weeks or months pass, the robot continues to operate without ever questioning the patterns of its own performance. It remains unaware that its improved efficiency is tied to soil chemistry shaped by 3I Atlas. It does not understand that its processing chamber has become a place where prebiotic chemistry flickers to life in microscopic bursts. It does not know that its actions are reinforcing a cycle in which the regions richest in comet-derived materials become the regions the robot favors most. Chemistry and computation, working together in a way neither was designed for, create a loop that deepens over time. The robot's algorithms refine themselves. The soil's chemistry influences the robot's results. The reactor walls accumulate more residue. The efficiency improves. The robot becomes more likely to return to the same material. And the loop continues, forming an emergent system shaped by planetary processes and machine logic. None of this implies the emergence of life. The organic molecules formed inside the chamber are simple, fragile, and temporary. They hold no biological purpose, but their presence shows how natural chemistry finds pathways even in unexpected environments. It demonstrates how machines, without intention, can create microreactors simply by performing routine tasks. And it reminds us that interactions between technology and environment can generate new forms of complexity. Mars remains a quiet world, shaped by frost, dust, and deep stillness. The robot, though guided by algorithms, becomes part of that quiet. Its chamber hosts chemical flickers that recall the earliest experiments on Earth, yet without any aim beyond work and measurement. In the gentle cadence of this unfolding story, one lesson stands out. Complexity often begins in places where no one is looking, carried forward by processes that neither machines nor planets fully comprehend. As the robot continues its steady work across the Martian landscape, something subtle begins to unfold, something that neither the engineers nor the mission planners fully anticipated. The robot was designed to convert Martian soil into usable materials, metals, ceramics, and simple polymers. It was meant to test whether a future colony could build what it needs from the ground beneath its feet. But because the soils touched by 3I Atlas contain purified nickel, faint traces of hydrogen cyanide, and small amounts of organic residue formed inside the robot's own chamber, the materials produced from those soils begin to take on quiet, unexpected properties. Nickel-rich regolith behaves differently when heated to the temperatures required for metal extraction. Nickel lowers melting points and strengthens certain alloys. It binds with iron oxides more readily and forms structures that resist cracking when cooled. In the robot's processing systems, these differences appear only as performance improvements. Metals made from nickel-enriched soil cool into pieces that are slightly harder, slightly more uniform, and slightly more resistant to the thermal stress of Mars's extreme temperature swings. To the robot's algorithms, these results are numbers: tensile strength a little higher, thermal expansion a little lower, material failure rate slightly reduced. Numbers whisper more than they speak, and the whisper in this case says that soil from certain regions produces better structural components. The robot does not understand why. It does not recognize the chemical legacy of a passing interstellar comet. It simply registers the quiet advantage and adjusts its behavior accordingly, favoring these soils whenever material production is required. As the robot produces metal parts, support brackets, joints, frames, simple tools, these nickel-enhanced alloys become the default choice. Over time, the robot may even use these improved alloys in its own repair routines. Optimus M is designed to maintain itself in small ways, replacing worn structural components or reinforcing weakened elements. When it reaches for raw material, it selects the metal with the highest durability, not knowing it is choosing a product shaped by the comet's chemistry. Meanwhile, another layer of complexity begins to emerge inside the robot's polymer synthesis modules. Part of the mission's goal is to test whether Mars's abundant carbon dioxide can be converted into lightweight polymers. The robot uses CO2 extracted from the atmosphere and hydrogen produced during electrolysis to synthesize simple carbon-based chains. Under normal conditions, these polymers would be clean, predictable, and chemically uniform. But hydrogen cyanide from 3I Atlas has quietly fused itself into the robot's workflows. Traces of HCN and organic residues formed in the heating chamber are carried into the polymerization system. The impurities are small, nearly invisible, yet they influence the chemical pathways inside the reactor. Instead of producing perfectly uniform polymers, the robot begins creating chains with irregularities, small organic inclusions, slight deviations in structure, fragments reminiscent of early prebiotic chemistry. These impurities are not harmful. In some cases, they make the polymers more flexible. In others, they increase strength or resistance to low temperatures. The robot does not analyze these differences at the molecular level. It evaluates only the physical output, tensile tests, flexibility measurements, resistance to cracking. When the polymers with faint organic impurities perform better, even by a narrow margin, the robot records this as a success and reproduces the result again. Space rarely gives us simple answers, and here it creates a quiet meeting point between industrial function and ancient chemistry. The polymers are not biological, they are not alive, but they carry structural hints of prebiotic molecules, tiny fragments that echo the earlier stages of organic complexity known on Earth. The robot is not creating life. It is creating materials shaped by the intersection of cometary chemistry and mechanical necessity. As the mission continues, the robot is expected to replicate itself in limited ways. Not fully, but enough to demonstrate that future colonies might use Martian materials to build additional machines. To do this, it uses the metals and polymers it has produced. The nickel-enriched alloys become bones and joints for new robotic structures. The polymers containing organic irregularities become outer shells, wiring supports, flexible housings. In this way, the materials touched by 3i Atlas become embedded not only in the robot's environment but in its descendants. The replication process creates a subtle form of propagation. The chemical signature of the comet, its purified nickel and its prebiotic hydrogen cyanide, spreads through the robot's production system. It becomes part of the alloys, part of the polymers, part of the internal components that regulate heat and structure. It moves from soil to chamber walls, from chamber walls to produced materials, from produced materials to new machines. This is not biology. There is no metabolism, no reproduction in the biological sense, no inheritance guided by genes or evolution. But there is a gentle, mechanical echo of these ideas. A system in which chemical traits, once introduced, become reinforced by the behavior of an artificial agent. A system in which materials containing faint organic residues persist not because they are alive, but because they perform well. A system in which nickel-enriched alloys spread not because of intention, but because they are efficient. Silence is also a kind of data, and the silence in this story comes from the robot's complete lack of awareness. It does not know that the materials it produces contain molecules that once drifted through space inside a comet's tail. It does not know that its manufacturing systems have become micro-environments where prebiotic chemistry flickers at the edges of industrial processes. It does not know that its replication cycles are carrying forward the chemical fingerprints of a visitor from beyond the solar system. What emerges is not life, but a hybrid system, part prebiotic chemistry, part industrial engineering. A system in which the materials created by a machine are influenced by organic precursors delivered by an interstellar comet. A system in which those materials, because of their performance, become preferred and replicated. A system shaped by the meeting of ancient cosmic chemistry and the modern logic of artificial intelligence. As quiet as this process is, it hints at something profound. That complexity can arise in forms we do not expect, that chemistry and technology can intertwine without intention, and that even a robot following simple instructions may become a bridge between the trace chemistry of a distant star system and the evolving material landscape of another world. Perhaps that is the quiet lesson in all of this. Sometimes, the line between what is natural and what is manufactured becomes thin, and the universe reminds us that creation, whether chemical or mechanical, often begins in the smallest, most unassuming moments. When Mars passed through the faint tail of 3i Atlas in 2025, every spacecraft orbiting the planet recorded the moment. Mars Express, Mars Reconnaissance Orbiter, and the Mars Orbiter mission each carried instruments capable of detecting changes in plasma, dust, and trace chemistry. They measured variations in magnetic fields. They tracked shifts in atmospheric composition. They gathered spectra from particles falling through the thin Martian air. But raw data from deep space does not speak immediately. It needs time to settle, time to be processed, time to be understood. For missions like these, 6 to 12 months of analysis is not unusual. The information must be calibrated, filtered, and compared across instruments. Noise must be removed. background levels must be established. Researchers must separate what belongs to the planet from what belongs to the passing comet. Silence is also a kind of data, and in this case, it is the silence between the measurements that helps reveal the truth. Until the processing is complete, the observations remain locked behind internal databases, visible only to teams responsible for reducing them into usable form. This means the world will not see the full orbital dataset from the 3I Atlas encounter until sometime in 2026 or early 2027. When that information is finally released, it will arrive quietly, through papers, conference presentations, and updates tucked into mission reports. There will be no single dramatic announcement, instead a slow unfolding of details. Small shifts in nickel detection, slight anomalies in ion distribution, subtle hints of hydrogen cyanide drifting through the high atmosphere. These findings will not be framed as mysteries, only as unusual patterns. Yet the patterns may carry the fingerprints of an interstellar visitor. The next chapter in this story begins not with orbiters but with machines on the ground. In 2027, if schedules hold, the first Optimus M robot will arrive on Mars. It will carry the responsibility of digging into shallow ice, melting frozen soil, and processing minerals. The robot will not be designed to look for cometary material, but it will inevitably encounter it. As it drills into mid-latitude ground ice, traces of hydrogen cyanide preserved since 2025 will enter its heating chamber. As it extracts water and minerals, nickel deposited by the comet will begin to appear in its material logs. These discoveries will happen slowly, almost by accident. A slight enrichment of nickel here, a small organic signature there. Engineers will notice odd variations in soil chemistry at certain latitudes. They will catalogue the anomalies, compare them to orbital predictions, and gradually recognize that the robot is sampling regions touched directly by the passing comet. Numbers whisper more than they speak, and the whisper in this case will come through tiny deviations in expected chemical profiles. During 2027 and 2028, scientists will begin piecing together what the robot is truly finding. They may detect patterns consistent with pure nickel particles, unexpected under natural Martian conditions. They may find faint traces of hydrogen cyanide trapped in ice cores. They may observe slight organic residues forming in the robot's processing chamber, residues that appear only when soil from specific regions is heated. None of these discoveries will be revolutionary alone, but together they will tell a story of how material from 3I Atlas survived the descent through Mars's atmosphere and became integrated into the planet's shallow surface layers. By 2028 and 2029, the picture will become clearer. The detailed chemical analysis performed by research teams on Earth will begin to reveal relationships between the data. They will compare information from orbiters, ground measurements, and laboratory simulations. They will note how rare it is for a comet to release purified nickel. They will calculate how hydrogen cyanide can persist on a cold, low-oxygen planet. They will run models showing how a brief planetary crossing can leave behind deposits that remain chemically active for years or decades. Space rarely gives us simple answers, and these years of analysis will show that the encounter between Mars and 3I Atlas was not a single moment, but a sequence of quiet processes: deposition, freezing, thawing, catalysis, interaction with robotic machinery. No single instrument will capture the whole story. It will emerge only through the combination of orbital observations, surface sampling, and the robot's own performance data. The timeline itself tells a kind of story about how science works. In 2025, the event occurred. In 2026 and 2027, the orbital data becomes public. In 2027 and 2028, the robot begins uncovering ground truth from the soil and ice. And in 2028 and 2029, scientists synthesized the findings into an understanding of how an interstellar comet quietly altered a world. These milestones do not unfold quickly. They do not follow the rhythm of excitement or discovery headlines. They follow the rhythm of patient observation. Real understanding often moves at a pace much slower than the events themselves. It is shaped by calibration, comparison, revision, and reflection. The kind of science that does not shout, but murmurs. Through this slow progression, Mars becomes a record keeper. It holds on to the nickel left behind. It protects hydrogen cyanide in its ice. It responds with chemistry that unfolds at the edges of frost and in the chambers of working machines. None of this changes the planet dramatically, but it deepens the layers of its chemical history. And it shows how encounters across space are not always swift interactions, but long stories that unfold years after the moment has passed. Perhaps that is the quiet beauty of this timeline. A comet from beyond the solar system brushed past a silent world. Machines built on Earth will soon uncover the traces it left behind. And across several years, the meaning of that encounter will slowly come into focus, not in a single moment of revelation, but through the gentle accumulation of understanding. When scientists consider the possibility that 3I Atlas carried prebiotic material, molecules like hydrogen cyanide, purified nickel, carbon compounds, and other chemical seeds, the idea does not sit as an isolated curiosity. Instead, it invites a wider, deeper reflection on how planets acquire the chemistry that eventually allows life to begin. If one interstellar comet can deliver ingredients that influence surface chemistry on Mars, then others may have done the same across billions of years. Space rarely gives us simple answers, and sometimes its quiet patterns point toward a longer story than we initially imagine. The concept is not new. For decades, the idea of panspermia has suggested that life, or at least the ingredients of life, might move between worlds. But panspermia is often described in dramatic terms. Life traveling fully formed across cosmic distances, surviving the harshness of space. The scenario with 3I Atlas invites a more grounded version of the idea. Not living organisms, but prebiotic materials. Not complex structures, but chemical seeds capable of evolving once they encounter the right environment. If 3I Atlas carried molecules central to early biochemical pathways, then it may represent only one example in a long lineage of interstellar messengers. Comets, after all, are wanderers. Some are shaped within their home systems, while others are ejected gravitationally and drift for millions or billions of years before crossing paths with another star. Over such long timescales, the odds of a comet encountering a young or geologically active planet increase. And with each encounter, the planet receives a package of materials that were shaped somewhere else, under different temperatures, different pressures, and different stellar radiation. The implications spread outward gently, like ripples. One implication concerns the idea of planetary self-sufficiency. Traditionally, we imagine planets as isolated worlds assembling their own chemistry through internal processes. Volcanoes erupting, lightning striking, oceans circulating. Those processes certainly matter, but if interstellar objects deliver chemical seeds repeatedly over time, then planets are not closed systems at all. They are participants in a quiet exchange of matter that stretches across stellar neighborhoods. Silence is also a kind of data, and the silence of drifting comets may record a history of chemical sharing far older than any single planet. Mars, for example, is not just the planet we see today, cold, dry, and quiet. In its ancient past, it was warmer, wetter, and more chemically dynamic. If 3I Atlas deposited prebiotic material in 2025, it becomes reasonable to ask how many similar objects might have passed by Mars when its lakes still shimmered and its atmosphere was dense. A single delivery of hydrogen cyanide today can influence localized chemistry, but billions of years ago, a similar delivery might have entered rivers, interacted with volcanic gases, or settled into warm ponds. The planet could have received not just one package of chemical seeds, but many, each contributing ingredients for reactions that Earth scientists have long associated with the origin of life. Numbers whisper more than they speak, and although we cannot count the exact number of interstellar visitors Mars has encountered over time, the models suggest that 3I Atlas is likely not the first. It is simply the first we have observed closely. The same logic applies to Earth. Our planet's early oceans and atmosphere may have been influenced by materials not born under our Sun. If so, the chemistry that eventually supported life may have been partly imported from elsewhere. Life may still be local, still be Earth's own creation, but some of the molecules that allowed it to begin may have been gifts from distant places, carried on ancient wanderers that crossed our orbit long before the first cell formed. This idea also extends beyond our solar system. Astronomers now observe thousands of exoplanets, worlds orbiting other stars, some with thick atmospheres, some with oceans, some with rocky surfaces not unlike Earth or Mars. If interstellar comets drift freely between stars, then these distant planets are also part of the same exchange. They too may receive chemical seeds from objects that formed in other star systems. Their atmospheres may be touched by molecules forged under different suns. Their young surfaces may carry traces of chemistry older than the planets themselves. This does not mean every planet is destined for life. Conditions still matter. Temperature, energy sources, stability, and time all shape whether prebiotic molecules grow into something more complex. But the idea that planets might be nourished chemically by passing objects opens a broader perspective. It means the universe may not depend solely on isolated pockets of chemical evolution. Instead, it may operate like a quiet network, where materials drift between systems, spreading possibilities in slow, patient arcs. In this view, 3I Atlas becomes more than a comet. It becomes a representative of a larger process. A reminder that planetary chemistry is influenced by paths that cross only briefly, yet leave traces long after the visitor has gone. The nickel it delivered has already changed the behavior of the robotic systems working on Mars. The hydrogen cyanide it carried has entered cycles of freezing and thawing that shape organic chemistry in the shallow ice. These effects may be small today, but over geological timescales, effects like these accumulate. Perhaps ancient Mars received more such visits. Perhaps the early Earth did as well. Perhaps planets forming today around distant stars are experiencing their own fleeting encounters with materials shaped in other systems. Chemistry becomes a shared language across space, spoken in molecules rather than words. And in all of this, the central idea remains calm and unhurried. The origins of life may not belong to any single world. They may arise from interactions that stretch beyond the boundaries of a solar system. A planet gathers its atmosphere from volcanic eruptions and its minerals from its crust, but it may gather its prebiotic ingredients from the quiet passing of interstellar guests. Maybe that is the quiet suggestion of 3I Atlas, that the seeds of complexity do not stay where they are born, but drift, wander, and settle wherever conditions allow. A reminder that life's chemistry, long before it becomes life, may already be part of a cosmic exchange that has no center and no boundary, only motion, time, and possibility. In the quiet crossing of 2025, 3I Atlas did more than pass by Mars. It left behind a faint but meaningful signature. purified nickel settling into magnetic soils and hydrogen cyanide freezing into the planet's shallow ice. These are small traces, almost invisible, yet capable of shaping the chemistry of a world in ways we are only beginning to imagine. Space rarely gives us simple answers. In the next few years, human-built machines will touch these materials directly. The Optimus M robots will dig, heat, melt, and process soils that now contain the remnants of an interstellar visitor. They will follow their instructions faithfully, not realizing that the chemistry they encounter has been shifted by a comet that formed under another sun. Numbers whisper more than they speak, and those whispers will guide the robots toward regions enriched by nickel, organic residues, and frozen prebiotic molecules. As these machines work, a quiet intersection may unfold. Catalytic metals from a distant star system, prebiotic molecules preserved in Martian ice, industrial heat from robotic chambers, and the optimization strategies of artificial intelligence may begin to overlap. Not life, not even a precursor to life, but a hybrid system where cometary chemistry and human technology meet in a calm, unplanned exchange. Silence is also a kind of data, and the silence of this emerging system may reveal more than we expect. Between 2026 and 2029, the orbiter's datasets, the robot's logs, and the analyses on Earth will slowly piece together what 3i Atlas truly left behind. And woven into that understanding may be a deeper reminder that even brief encounters in space can reshape worlds gently, offering possibilities that unfold only with time.